Okay, guys. So good evening to all of you. So last time we started to look at hardness of like super polynomial hardness. So rather than talking about just FPT hardness, I thought that let's talk about super polynomial hardness. How do people show this kind of hardness in this kind of regime? Okay. So we will see various kind of hardness, and we started with normal, what do you call normal hardness for 3 sets. So what is P time means, like what is NP hardness means, like some of the problems cannot be solved in polynomial time. They're like SAT, 3 sat, right? And what does this mean? Then we talked about a little bit about what parameterized reduction could or should mean. Okay. And then we moved on, like why vertex cover to independent set the normal reduction is not a parameterized reduction. Okay. And then we said that, okay, so the one problem which we will assume to build our hypothesis for W1 W1 hardness or the FPT intractability is basically that click does not have f of k poly time algorithm, or in other words, and the moment you assume this, you can trivially show that click hypothesis fails. That is, independent set does not have f of k poly time algorithm. Okay. And then we say that there's nothing about any of these problems. You could start with any problem for which there has not been any progress and say that, look, maybe this running time is optimal, because if we could improve this running time, then there are a bunch of problems for which we could improve the running time. That is, the running time of these problems, they fall together, like they rise or fall together. Okay. And so people have actually built a world around APSP. So if someone is interested, I can send you a paper which does some of these things. Okay. And then we moved on to what is called exponential time hypothesis, which tells that 3 sat cannot be solved to the power little of n time. And then I gave an assignment, which was a real assignment, whether for 3 sat you can get 2 minus epsilon to the power n time algorithm for 3 sat or not. Okay, so this was, we'll come back to that. Okay. And then we talked about SAT when there's no restriction on clause length, and then there's a 2 power n algorithm, brute force, and we asked 2 minus epsilon to the power n algorithm for SAT. We do not know. So SAT does not admit an algorithm with running time 2 minus epsilon to the power n, and this is what is called a strong exponential time hypothesis. Okay. So there is the ETA, there is the click hypothesis, and assuming set, we said that hitting set cannot be done better than 2 to the power universe by 2, basically. Okay. And then we talked about diameter problem, for which I did not give you reduction. Then we talked about this classical reduction from 3 sat to vertex cover, but based on that reduction, we can only rule out n to the power 1 by 3 minus epsilon time of algorithm. So now let's look at the world we live in. Okay, so what is this? So first is 3 sat does not have, what's the date today? Today is 17th, right? Okay. Does not have polynomial time algorithm. Okay. That is whatever classical P not equal to NP assumption. Okay. Secondly, we said 3 sat does not have 3 sat does not have 2 to the power little of n time algorithm. Okay. N is number of variables. And third, we assumed SAT does not have 2 minus epsilon to the power n to the power big of 1 time. It doesn't matter. This is irrelevant. Okay. And this is what is known as exponential time hypothesis. This is known as strong exponential time hypothesis. Okay. So for now, for all of us, and then of course, we have this click hypothesis, which says that click does not have f of k n to the power 1 time algorithm. Unless, okay, some class. Okay, if PT is this, W1 is all these problems for which you do not have such algorithm. Okay, so we had some such assumptions and we started to do some of the things. Now notice, look at a vertex cover. Like after a lot of hard work, all we have seen for vertex cover, what kind of algorithm that we have seen for vertex cover? So much of hard work, where n is number of variables, number of vertices. What kind of algorithm we saw? Anybody? No, like we are talking about in terms of exact algorithms. Okay. So what kind of algorithms we have seen in the class?
So 1.28 or to the power n.
Right. Okay. But isn't it very natural to ask, what about an algorithm which is running time, say, n divided by log square n? That's such an algorithm exists, right? Because asymptotically, this is much better than this, right? This algorithm. Right?
Yes.
So our question will be, assuming one of these stronger hypotheses like ETH, SETH, right? Assuming that some of these problems do not have good algorithm like 3SAT or SAT, can be ruled out. Okay, so what is our appropriate mode question is the following. Assuming impossibility of certain kind of algorithms for SAT or SAT, 3SAT, can we show that vertex cover does not have 2 to the power big O of n log square n time algorithm? Okay. Or more generally, no 2 to the power little of n time algorithm. Last time, what did we show? Do you remember the reduction which we did last time from 3SAT? I think Pratik told the reduction or someone. I don't know. Right? So we had this, remember, we had x1 bar, x2 bar, so on and so forth, xn and xn bar. And for every 3 clause, suppose we had a clause A or bar or C, we made A, B, C, and we connected it to some A here, suppose, B bar. So somewhere B bar and C bar. Remember this reduction?
Yes.
Okay. Now notice what happened in this reduction is that look at n number of variables here and m number of clauses here. Now in this graph, what is the number of vertices? Right? The number of vertices that becomes, okay, so this was an NP-hard reduction. I don't care about anything else, but I just care about the number of vertices because that is our parameter of our interest. So notice how many vertices this graph has? 2n plus
2n plus 3m.
Now we know that 2 power little of n time algorithm does not exist for 3SAT. Okay, this is what we know. Now, assuming this, what can I say about vertex cover using this reduction? What can I say about vertex cover? What kind of algorithm vertex cover will not have? Because if we have such an algorithm, then using this reduction, we can get a better algorithm for 3SAT. So what is that running time? Is the question clear to all of you people what I'm asking? Okay. So please tell me, suppose if we have 2 to the power big O of n to the power 1/4 algorithm for vertex cover, where n is number of vertices, then what will happen? What will happen using this reduction? What kind of algorithm can we get for 3 set? Right? What algorithm can we make for 3 set using this nice algorithm for vertex cover?
To power little o of n.
To the power
Big O of n by 4.
What are you saying? You cannot have?
So if we have a 2 power big O of n power 1 by 4, then this will imply a 2 power big O of n power 1 by 4 algorithm for 3 set.
Why?
It should be n to the power 1 by 8.
Here's your reduction.
2n plus tm by 4.
Here it is. Everything is here.
Value of m is first 3 cube.
n
Cube, sorry.
n cube by 4.
What?
N to the power 3 by 4.
Okay. So what can SAT do? Look. Here's your 3 SAT. Okay. Here it is. It reduces to an instance. Suppose this is a phi. It reduces to instance G, and there is some K also, doesn't matter, such that vertex set of G is equal to 2n plus 3m, which is like 2n. So our n prime, which is Vg, is equal to how much? It is like 3 times, maybe at most n cube. So this is like order n cube, right? Now, for a vertex cover, we have algorithm with running time 2 to the power big O of n to the power 1/4, right? Now, what does this imply? 2 to the power big O of n to the power 3 times 1/4, right? So we made an algorithm for a vertex cover like this. We can solve this instance of vertex cover in running time this, and then in poly time, check whether phi is satisfiable or not, right? Right. So what did we get from here? Right. So we saw what kind of algorithm did we make. Using this, we made an algorithm for 3 SAT running in time 2 to the power big O of n to the power 3/4. And notice, but this is definitely not possible for 3 SAT. So such a running time for vertex cover shouldn't be possible. Am I right? So what does this imply? Implies a implies faster algorithm for 3 SAT, implies no faster algorithm for VC, right? So in particular, we cannot have these kind of algorithm. But suppose, can we have an algorithm with running time 1/3 minus epsilon? you will notice that even this is not possible. Okay, this is not possible. Okay, fine. Okay, so now let's look at the same reduction, but okay, let's look at the same reduction. Somehow we can prove, if somehow we can prove that 3SAT does not have 2 to the power little of n plus m time algorithm. Suppose this is say ETH prime. Then what can I say? If I had such, then what will this reduction imply? If I had even, if I would have assumed that 3SAT cannot even have 2 to the power little of n plus m time algorithm, then what will this reduction imply? Anybody? Anybody? Using this reduction, what can you suppose if I assume this, what can you rule out from this reduction? Okay. Prateek?
Hello.
Yeah. What do you think? What can we rule out from here? Suppose
Is it
you
2
had,
raised to big of n raised to 1 minus epsilon?
no, look at this. Suppose you had 2 to the power little o of n time. There's nothing, please guys, just like suppose we had 2 to the power little of n time algorithm for vertex cover. Then what will happen? You start with 3SAT, which is phi. And what are you introducing? Some g and k. What is the vertex set here? Is some 2 times n plus 3m, which is like 3 times n plus m. Is that fine? Okay. Now on this, suppose I apply 2 to the power little of n prime algorithm. What is this? This is implying some 2 to the power little of n plus m algorithm. Is that okay? Because n prime is 3 times n plus m. Is this fine with everybody? If yes, please put +1. Otherwise, please ask, because this is the crux of these things. I mean, if we do not understand these things, then like then we will have difficulty in doing this super polynomial time reductions. Okay. Okay. So if we assume, so what we learned from here? What did we learn from here? If we assume that 3SAT does not have 2 to the power little of n plus m time algorithm, implies vertex cover does not have 2 to the power little of n time algorithm. Is this fine? Like, do you all agree to this conclusion? Okay.
Yes.
Okay. So now it all boils down to, okay, so now let's just play the game here. Okay, so what is the game here? So now we assumed ETH that no 2 to the power little of n time algorithm for 3SAT. Am I right? But the most useful thing seems to be ETH prime, which is no 2 to the power little of n plus m time algorithm for 3SAT. Okay, you get my point? This seems useful, right? This is a useful statement because now if you notice, if you go through most of the NP hardness reduction, this will help you, like immediately it will start implying such kind of non-trivial upper bound or tight upper bound and lower bound on the algorithmic complexity. Okay, here, what is n? Okay, n is number of variables and m is number of clauses. Okay. Okay. Okay, is that fine? Okay, now, do you agree? ETH prime will imply ETH, right? If you can't have even 2 to the power little of n plus m time algorithm, then definitely you cannot have 2 power little of n time algorithm. Is that okay? So this seems fine, no? That no 2 to the power little of n plus m implies no 2 to the power little of n. Look, I'm still not talking about very precise things, but just get it in the system first. Okay. Okay. So is this direction of statement okay?
Yes.
Okay. You know what is surprising? This is what's surprising is. Surprising is ETH implies ETH prime. That is surprising. Okay, and this is a theorem. This is not something which, this is not an assumption. Okay, this is not an assumption. Okay, this is not an assumption. Okay, so I don't know how many of you know, but like this is based on, like this is what the theory is based on. This is something, a very non-trivial theorem called Specification. Okay, so what is an Specification? Okay, basically what it tells us that you start with any DSAT formula. Okay, so you suppose you give me input any DSAT formula. Okay, any DSAT formula is my input. Okay, let me not at least tell you something much more concretely. Okay, Okay, so now you give me okay, so here's an algorithm which does the following. What's the algorithm? It takes as input, okay, it takes as input an epsilon greater than equal to 0 and some positive integer q, okay, and if you give him a QCNF formula, okay, what is it going to output? It's going to output a family of formulas, okay, family of formulae, okay. So like family of formulas psi 1 to psi, say t. I will tell you what it is. And what is the property, first of all, that QCNA formula, say phi. So phi is satisfiable if and only if there exists I in 1 to t such that psi I is satisfiable. Okay. So I'm saying that, okay, given this formula, I will produce lots of formulas, T formula, so that my formula is satisfiable if and only if these guys are satisfiable. Okay. Is it clear? I mean, up until now, we have done nothing, but is the idea clear? So what does this algorithm takes? It takes a formula and it outputs many more formulas and say, look, I am satisfiable if and only if one of these formulas is satisfiable. Okay. Is that fine? Okay. Okay. And the properties are, what is the property? First of all, that have the same variable set as what is that called? As phi. Okay, that's the first thing. So how many variables they have? Number of variables is equal to n. But what is the funky thing is that number of clauses is at most k times n, where k is some function of epsilon comma q. Okay, so how many number of clauses it has? So at most a function of epsilon and q. So if q is 3, it's like some function of epsilon only number of clauses is there. Okay, do you understand? So this is why I'm going to call it, it's called sparsification, that you might have started with n to the power d number of clauses, but what is the property? That each formula that I have output, okay, is sparse, has order n number of clauses. Is that fine? Okay. And more importantly, how many such formulas will be generated? How many such formulas? Okay. So the number of such formula is t equal to at most some 2 to the power epsilon n, right? So if it's up to you, so if you give me epsilon, then I will produce you. So what is happening? Okay. So here is psi. I am producing how many? 2 to the power epsilon n number of clauses psi t, such that psi is satisfiable if and only if one of psi I is satisfiable. Okay. And each psi I has at most some kn clauses. Okay. Is that fine? Is the statement fine to all of you people?
Yes.
Okay. Okay. So what is this algorithm doing? Let's try to understand. This is like very crux of everything. So please understand, even we don't have to go into, we are not going to give a proof for this. If you want, I can make a proof some other day. It will require some 5-6 hours. Okay. But it's a very beautiful branching algorithm. So what is this? It's an algorithm which basically, think of this way. In sub-exponential time, I produce sub-exponentially many, like in 2 to the power little o of n time, I produce 2 power little of n number of formulae such that each formula is sparse and my initial formula is satisfiable if and only if one of these formulae is satisfiable. Okay. Now, once we have this sparsification, what will I do? I said, okay, fine. Now I have taken some 2 to the power little of n time and produced 2 to the power little of n number of formulas. And to solve each of them, how much I'm going to take? I have 2 to the power little of n plus m algorithm, right? So now I will take another 2 to the power little of n plus kn time, right? Because this is what I assume, that I have an algorithm which can do in n plus m time. And using this, I wanted to design a 2 to the power little of n algorithm. So to do that, what I did, okay, fine. I want to solve my problem in 2 to the power little of n time. Let me take sub-exponential amount of time, produce sub-exponentially many formulae, but the property is that each formula that I will produce at the end is sparse, has linear number of clauses. Once I have linear number of clauses, 2 to the power little of n plus m is amazing, because that is still 2 to the power little of n, right? So this is what I will, at this point of time, I will run this algorithm and then get a 2 power little of n time algorithm for 3 SETH. So what I did, so I'm saying to you that I will give an algorithm. Okay, so what does the algorithm does? Okay, so it starts with 3 SETH, right? What is its job? 2 power little of n time algorithm is job. And what it is assuming that this algorithm exists. So what I first do, okay, fine. Let me take 2 power little of n time and 2 power little of n number of formula I produce. So many, t of them. Okay. Now on each of them, what will I apply? I will apply this algorithm here, right? But what is the property now? The running time is 2 to the power little of n plus some k, but k is some constant which only depends on epsilon or something, doesn't matter. So this is also 2 power little of n. So 2 power little of n times 2 power little of n is 2 power little of n, right? So of course you have to do this epsilon properly, but that's an idea, right? So this is a non-trivial theorem or non-trivial algorithm that given, imagine, right? A Q formula could have n to the power q clauses and it produces you lots of formulas, but the number of clauses is like depends only on function of q and epsilon, right? So this is why it's a very beautiful theorem. It's a theorem, and if we will have time, we will prove this somehow. Okay, so this theorem allows us to assume that what is ETH? So ETH is basically there is no algorithm for 3 SETH running in time to the power little of n plus m. Is that fine? Is it okay with everybody?
Yes.
Okay, so now we all are literate with new knowledge that no, if someone tells you ETH, SETH, and you hear some of these things in talk, this is what it means. And why many of these reductions give us the desired kind of lower bound, because of this, that it's not 2 to the power little of n, but it's 2 to the power little of n plus m is not possible. And this is proved using the fact. So how do you prove? This is proved using sparsification. And now you understand why it is called a sparsification. Okay. Okay, so if I ask you guys, imagine that I have a graph G. Okay, graph G. Okay. Now graph G could have how many n vertices and how many edges? N square edges. Okay, and suppose I'm looking for I want to give a reduction onto bunch of instances. Okay, bunch of instances where just to give you intuition why this kind of things are true. Bunch of instances. So G is an yes instance if and only if one of these guys are yes instance. Okay. And each of them contains linear number of edges. Right. So what can you do? So you first do, look, so the idea is that, look, if I have a very high degree vertex, okay, if I have a very high degree vertices, then the number of vertices that drops in one side is very high. So those kind of branching can only go. So imagine yourself that other side had root n, degree is root n. How many such branching can you do? It's like something like 2 to the power big of root n times, right? So basically what happens that the moment you have more degrees, okay, the branching factor is more, but the depth of the tree is shallow. So you have to do this balance. And when the depth will become larger, then by the time you will reach that stage, your degree will be bounded. And that is the kind of idea we will have to apply even for SAT. Oh, is this variable appears in many clauses? If the variables appears in many clauses, then let's just set it to true or false, and then let's see what happens. Okay, so it will be very beautiful to state our statement for vertex cover formally and try to prove a specification for vertex cover. And if some of you are interested, someday we can just sit down together and try to prove it formally. Okay, but that's an idea that what happens that when you are branching on a very high degree vertex, then in one side you lose far too many edges. So that branch cannot take you too far. Okay, and only time when the branch takes you too far, when you are making little progress, but at that point of time, maximum degree of the graph is bounded. And if the maximum degree of the graph is bounded, you already have got a sparse graph. Okay, so is the intuition a little bit clear to all of you?
Yes.
Okay, I have not tried to prove anything formally at this point of time. Okay, but like I still want you to have a big overall picture of how these things are placed in a big picture. And like in the first course, even if you do not understand the technically how these things are proved, having a big picture is a very helpful thing. Okay, and at the right time we will prove these things very precisely with respect to epsilon and everything. But just to respect the theory, just to appreciate the theory, it is important that these things people have built over a period of time. Okay. Okay, so I will go back to making some reductions now. Okay, and so now we just now showed the following theorem. There is no 2 to the power little of n time algorithm for vertex cover unless ETH fails, right? Is that fine? Do you agree to this statement now? Okay. I want to prove the following theorem. And this you all will prove. There is no 2 to the power little of k time algorithm for vertex covered parametrized by solution size unless ETH fails. Is this fine? How many of you agree to this statement? Okay, both are here. This is obvious.
Isn't the first theorem implies the second?
Yes, but why? You're right. But
If we have a 2 to the power little of k algorithm, then
then
We can use that algorithm to design the 2 to the power little of n algorithm.
yes, because k is upper bounded by
And
n, correct, right? So, right? So clearly, theorem 1 implies theorem 2 as k is less than or equal to n. Is that fine? Okay. So what have we proved? We have shown our first result that we have been working hard for so long is asymptotically tight, right? So whatever algorithm we have built for vertex cover in the first half, at least asymptotically we cannot do better than that. Am I right?
yes.
Okay, good. Fine. Okay. Okay. And okay. Now I'll go back and try to show you some reductions and like we'll find connections between these objects more and more. Okay. So the first thing we assume in our world is that click is hard, right? And when I say now hard will mean no f of k n to the power big of 1 time algorithm. Okay. So from now onwards, whenever I mean hard, it will mean this, or which is equivalently means no FPT algorithm. Okay. Hard means this. Okay. And from click, what is our first reduction we showed? To independent set. Okay. Now we wrote a book. Let me go back to the book and see what other reductions we did. Then we'll do one by one. We will do some amazing reductions, don't worry. It will be fun. If you like reduction, it will be fun. If you don't like reduction, it could be boring. It's up to you. Okay. 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 So one thing which we'll show now is that I want to show following theorem, which is, so we'll keep coming to this chart and keep adding problems. Okay. So I want to show the following theorem that click on regular graphs is W1 hard. Okay. Whatever that means. Okay. And what is W1 hard? A problem is called W1 hard if it is in the same equivalence class as click. Okay. Okay. Okay, fine. So click on regular graph is hard, or click on regular graph does not admit an FP, like, so, okay, or rather, let's say another thing we can say, problem is called W1 hard if it does not admit f of k n to the power 1 algorithm when parameterized by k. Okay, so click on regular graph is W1 hard parameterized by solution sets. How can you show this? Okay, so we have assumed that click does not admit such an algorithm, but graph may not have the same degree. I want to show that the click, when every vertex is the same degree, still does not contain, does not have an FPT algorithm. Okay, so I want to give a reduction from click. Any idea? So I basically want to give a reduction from click to click on regular graphs. So what is the left hand side instance? G comma K. You have to come up with some G prime K prime such that every vertex in G prime has same degree. Okay, that's the first thing. And secondly, K prime, it's some function of K. Running time of this algorithm, it's say some G of K n to the power big of 1, right? I mean, it could be just polynomial also. And such that, what is the property? G comma K has a clique of size K if and only if G prime has a clique of size K prime. So this is what I want you to come up with. Okay, so I wrote down all the property that I desire from this reduction. Okay, just to make your life easy so that you can think, we will give actually a poly time reduction. Okay, and K prime will be equal to K. So it's just a normal polynomial time reduction. So give a reduction or click a polynomial time NP completeness reduction itself you give me, okay? To show that click is also NP hard on, so forget about this. Show me that click is NP hard on regular class. I know some of you like reductions quite a lot, so. Okay, thou shall make. Okay, so here's your here's your G and K, and let D be the maximum degree of the a vertex in G. Okay. What can you do? Here's a G. What should I do to make this graph? Okay, so rather than do this, what I do is that I take a copy, D copy of G. So this is G1, GD, and they are just basically equal to G. Okay, so they're disjoint copies. Now what I do, look at a vertex V here, which is going to appear here. Okay, and I'm going to have a cluster here. Okay, and how many vertex do that this cluster will have? How many? Suppose this vertex has degree X. So I will have D minus degree of V vertex. Okay, here. And I will make this V adjacent to everybody here. Okay. Similarly, this V will be at. Similarly, he will be adjacent to same guy. Like same vertex V will be, and similarly, this guy will be adjacent to. So now tell me, what is the degree of this vertex? What is the vertex degree here?
D.
dV, right? Inside. And now it is more adjacent to how much? D minus dV, right? So its total degree is now, this particular vertex V has total degree how much? What is the degree of this vertex now in this graph?
D.
D. What is the degree of this vertex in this graph?
All D.
Everybody has D. And what is the degree of this vertex? What is the degree of this vertex?
D.
Correct. So now for every vertex, we'll make such clusters, okay? And do the same thing. Okay. And that's my end of my construction.
Your cluster means independent set.
Yes. When I say cluster, like for every vertex, I will, so for every vertex, I will add for every vertex V in VG, add D minus DV vertices and make them adjacent as said. Okay, this is what we will do. Okay, now at the end of the day, what is, so now this is my G prime. Okay, so what is the property of G prime? Every vertex in G prime has degree exactly equal to D. Okay. Hello.
Yes.
Okay. Okay. So, okay. So now what does this implies? Okay. So now I want to say that G comma K is a yes instance if and only if G prime K is a yes instance. Okay. Which direction is trivial?
Forward
If,
direction.
yeah, if G has a click of size K, take it in any copy. Okay. Now reverse direction. Suppose assume that K is greater than or equal to 3. What is the meaning of this? And suppose K is greater than or equal to 3 and let C be a click in G prime. Okay. My claim, C cannot contain any newly added vertices. What I mean by this, or let's say, let's call this, these vertices that we added, let's say newly added vertices. Why? Why will it not contain? Look at any vertex here. What is their neighborhood? Their neighborhood is an independent set. Because every vertex has one neighbor in each copy of G. Right? Is that okay?
Yes.
Yes.
Right? So for every vertex here, look at their neighbors. Their neighbors belong to every class. So that's like independent set. But if you're talking about a click, every vertex at least participates into a triangle, right? Because K is greater than or equal to 3. Right? Why? So proof, no newly added vertex participates into any triangle as their neighborhood is an independent set. So what does it imply? This implies C belongs to some GI, but GI is same as G, which implies C is a click in G. And now you can ask, why are we assuming K is greater than or equal to 3? Because if K is less than or equal to 3, K equal to 2, then we can solve this problem in polytime anyway. So you can assume that K is greater than or equal to 3. Right? So click on regular graph is W1 hard parameterized by solution size when K is greater than or equal to 3. Is that okay? Anybody has any? And this is a parameterized reduction. Actually, it's a polytime reduction that preserves the parameters. Should I tell some other reduction? Okay. Okay, so the one reduction that I want to talk about is another reduction. This is a very famous problem, and it helps us. It's called multicolor click, or this is also called partition click. Partitioned click. Okay. So what is the problem? So your input is graph G, where vertex set is partitioned into V1 to Vk and comma k. So in fact, V1, V2, Vk are independent sets. It doesn't matter, but they're independent sets. And my parameter is k. And question is, does G have a click of size k, or does G has a click containing at least one vertex from each class? Okay. Is this fine? Right? So what is a multicolor click? So basically you're given this partition of vertex set, and you are supposed to pick up vertex each from each, and so that they form click among themselves. Right? Is the question clear to everybody?
Yes.
Okay. So please put +1. Let me see how many of you have understood the question at least.
Would you go up?
Okay, Pratik, here.
Yeah.
Is fine?
Yeah. Got it.
Or even more further?
No, that's
Okay. So let's give a reduction from click to partition click, which is bit nice. And then we will do some even easy one. Okay. Click to multicolor click. Okay. So let's say, assume has f of k into the power big of 1 time algorithm. Okay. Then I'm going to design an algorithm for click in FPT. Is the goal clear? So I'm going to say that, look, we do not believe that click has such an algorithm, but if you multicolor click had such an algorithm, then I could design such an algorithm for click. Is that fine? Is that okay? The goal? Okay. So now, very simple. Okay. Process. Here's my random process. Okay. Random process. Okay. Suppose I randomly assign, okay, f is a function that assigns a vertex v in Vg, an integer from 1 to k with probability 1 over k. Is that okay? Is the random process fine? Okay. So now please tell me, suppose G has a click. Okay. What is the probability? Suppose G has a click of size k. What is the probability that vertices of C have got distinct colors? Okay. Or in other words, now look at these V1, V2, Vk, right? So these are like those. This is F inverse of 1, F inverse of 2, this is F inverse of k. Okay. And I'm asking, what is the probability that for all what is the probability that for all I, Vi intersection C is exactly equal to 1? This is all that. What is the probability of this? Can anybody do this probability for me? Like, do you understand what my random process was? We have just randomly assigned an integer from 1 to k each vertex. And now I'm saying that I have a clique of size k. What is the probability that clique, like every part contains exactly one vertex of this clique? What is the probability of that?
K
factorial
factorial by k to the k.
What is the probability that C is colorful? What did you say?
1
Is
by
this
e
correct?
power k.
Is this okay? Which is like at least 1 over e power k. Okay. But now, after doing this, what can I do? What did I get? I can delete all the edges here, delete all the edges here, delete all the edges here, delete all the edges here. And now what is an instance? What is this instance of? What instance did we get now?
Multicolor clique.
Exactly. Right? So after doing this, we get an instance of multi-color clique. MCC, let's call it MCC, multi-color clique. Okay? Is that fine? So now, if now we can apply what we can do after getting this reduction, we can apply FPT algorithm for multicolor clique and then get an FPT algorithm for clique, okay, with probability of success 1 over e power k. So to boost, we should do this experiment and plus FPT algorithm for multicolor clique. How many times? How many times should we run this experiment so that the probability of success is constant?
E power k.
Exactly. So in e power k times FPT time for multicolor clique, okay, equal to FPT algorithm for clique with probability of success, say at least half, right? So we can, and the point is, irrespective of all that. So this implies that we cannot have such an algorithm for clique, multicolor clique, right? Otherwise, we can get a randomized FPT algorithm for clique. So if we also assume that clique does not have randomized FPT algorithm, then we will be good. But we don't need to assume that because we can replace this function, okay, this function VG21 2k, we can replace this function by this random process by functions of size e power k n with a property that there exists for any set S, there is some function which will make it colorful. So we don't have to, but let's just, all I want to tell you that you should also think. So in some sense, this is a reduction. How much time does this reduction takes? Reduction itself takes how much time? FPT time. Right? Okay. So what we have been able to say, we have been able to show that theorem, unless clique has FPT, unless clique has FPT algorithm, multicolor clique does not have FPT algorithm. Okay. So is this fine? The reduction fine? Pratik, is it fine? Have you seen these kind of reductions before? These kind of randomized reductions?
No.
Okay, good. So that's all that my point was, that to show you that these kind of things can also be used in reductions. Okay, and reduction does not always has to be many to one reduction. It could be just Turing reduction, meaning if you have an algorithm for this, I can design such an algorithm, and hence such algorithm may not exist. Okay, but now I want to prove to you like much more simple. I mean, I on purpose I went and showed all of you people this just to give you an exposition of what this coloring functions or what hash functions can do for us. Okay. So here's another theorem that we want to prove. What we want to prove now is the following. So there is a parameterized reduction from, in fact, click on regular graphs to multicolor click on regular graphs. Okay. Okay, let me write down what it will. We'll start from G comma K regular. Okay. And we'll make G prime actually K. Okay. Regular plus multicolor. And this will take polytime. Normal. So now please tell me, because you people are much better than me in making normal polytime reductions. Just like NP hard reduction. Okay. Okay. So suppose G is like, okay, V and N vertices. Okay. Now what we are going to do, we are going to have K vertexes. So we will have, basically this will be like V1, 1, V1, V2, 1, Vn1, V1, 2, V2, 2, Vn2, V1k, Vnk. Okay, is that fine? So for each vertex here, we have made k copies. Okay. Now, how will we give an edge? So if suppose U and V are adjacent in G, then what will I do is that suppose there are two vertex U and V are adjacent. Okay, then you go look at some A and some B copies of these guys. Okay, ith copies and some bth copy of these guys. And what will you do? You just make them adjacent. Okay, so now here, suppose this vertex will be adjacent to all the vertices in this guy that it is adjacent to. That's it. So look at the original graph. Which all vertices he's adjacent to? So he's going to be adjacent to all those vertices, the same copy in each class. So what is the degree of each vertex now? What is the degree of each vertex? Degree of each vertex in G prime. What is this?
K times the degree of the G.
So suppose that is R. So what it is?
KR.
It is K into R. I think it is. It should not be KR. It should be. I think it should be K minus 1. No, because look, this guy is not adjacent to vertices in its own class. No, it is only adjacent to vertices in other classes.
Yes, yes.
Right, right. So so it is adjacent to R vertices in each of the classes except itself. So it is K minus 1 into R. Okay. So what is our claim? So is the reduction fine? What did we started with? We started with a graph G. We made K we made K independent sets, each containing one vertex each corresponding to my graph. So each class had n vertices each. Now we picked up a vertex in the class and we said, oh, you represent this particular vertex in my old graph. Let me look at your neighbors. So these set of vertices are your neighbors. Let me make you adjacent to these set of neighbors in each of other color classes. Okay, that's all the construction is. And this we do it for every vertex in every class. Okay, is that okay with everybody?
Yes.
Okay. Okay, so now what I want to show is that following. Okay. What do we claim? We claim that G has K click if and only if G prime has K click with exactly one vertex from each VI. Is that okay? Okay. Now, suppose V1, V2, dot, dot, Vk are vertices in G that form click. So what we can took V11, V22, tick. What will this happen? What will they form? Do they form a click? This is
Yes.
the first vertex copy here. He's definitely adjacent to all its neighbors, in particular to be in each of the classes. So in particular, in the second class, he's adjacent to him, and the kth class, he's adjacent to him, right? And this is true about everybody. So, okay, then this forms a click in G prime that contains exactly one vertex from each class. Is that okay? Now what we show? Now conversely, suppose suppose G prime has K click. Okay. Now, how do they have click? So suppose they have, like, say, again, let's just assume for V11, okay, V22, VKK. Okay. It's a K click in G. Okay. Now, correspondingly, consider V1, V2, Vk in G. Okay. Now, by definition of G, what we know by definition of G prime, okay, VIA and some VJB are adjacent if and only if VI and VJ are adjacent, and that's it. So is it fine that they induce, therefore these vertices induce a click in G, and therefore V1, V2, Vk induces click in G, right? So this is very like if you make some reductions on bipartite graph from general graph, no, this is the most natural way to give the reduction. Is that so? Can you show me that for dominating set, right? Do you know what dominating set is? Okay. Yes. So what is input is G, K, okay? And let's not forget about parameter. We are not talking about parameter, okay? Does there exist set S subset of VG, okay, such that closed neighborhood of S equal to VG. In other words, what is the meaning of this? Given a set S, for every vertex V, either V belongs to S or neighborhood of V intersection S is not equal to empty. Right? That's all. So it's very different from vertex cover. So it's basically set of vertices. So every vertex either belongs to the set or has a neighbor inside this. So for example, this is a dominating set. Okay, the single vertex is a dominating set. Okay, so now suppose you assume that dominating set, so it is known that dominating set is NP complete on general graph. Okay, assuming this, show that, and this I'm not going to show, I want you to do now, and now, some of you, dominating set on bipartite graph is NP complete. Can someone of you give me a reduction? So all I'm saying is that you can assume that dominating set is NP complete on general graph. Assuming this, can you give me a reduction which shows that dominating set on bipartite graph is NP complete? In other words, I'm saying you start with a general graph, an instance of dominating set, and give me an instance for dominating set where the input becomes bipartite.
So in one side, all the vertices is there. Other side, same vertices set, and we'll make the, we keep that adjacency. Means Vi, Vj is adjacent, then we'll make then A and A is there. Now we taken one extra vertex.
Okay, wait. So what he's saying is that given a graph G, K, okay, so now he basically, suppose this has VG, has n vertex, so he takes, okay, you keep two sides, okay, suppose I do the same thing, V1 to Vn, 1, and V1 to Vn 2, okay. Now, is that fine? This is what you want to do,
Yes.
want me to do? Now, what do you want me to do?
If
Suppose I have Vi, Vj edge in G, what should I do now?
Vi dash Vi1 Vj2 Vj1 Vi2.
Okay, just to let's make our life easier, because just two copy. So let's say, let's not do this. Okay, it's just 2 and all becomes, it's okay when we have. So suppose this, and now before every vertex we make U1 to E1 and W1 to W1. So for each Vi, we have two copies, Ui and Wi. Okay, so now what are you saying? Tell me. So if I have a Vi, Vj edge, what should I do?
Ui Wj, Uj Wi.
Ui
Wj.
Or rather, why don't I say for every vertex, I look at their neighbors. For each vertex, I add edges to its neighbors in the other side.
Closed neighbor.
Close neighbor. Okay. What is the meaning of close neighbor?
Means Ui to Wi should be there.
Okay. So what he says that suppose Vi has neighbor. Suppose Vi has neighbor some. Okay. So you go to Ui and go to all its neighbors in the other side, give an edge. Okay. Plus you also give an edge this. Okay. Now what should I do?
Now one extra vertex and make adjacent to all UI.
Okay. Now make an extra vertex here, and you are going to give him, make him adjacent to everybody. Fine. Now what should I do? Is
That
this
is-
end?
Yes.
Okay. So what's
GK G dash K plus 1.
okay, first wait. Is everybody okay with the reduction? I'm not talking about correctness, just the reduction. What we constructed. Okay. Now I need someone else. Okay, not you, Satya. Okay. Okay. So what he's saying, G comma K is a yes instance if and only if G prime comma K plus 1 is a yes instance. Anybody else can show me, can explain to me this, or to everybody else?
So if
And then, yes, tell me.
so if V1, V2, Vk is a dominating set,
Hmm?
then the same
What-
set.
What you are saying? Wait. So let's say V1, V2, Vk is a DOM set in G. Then
U1, U2,
UK.
this will dominate the right hand set, like W1 set thing.
Will dominate
The right
every
hand.
vertex in say every vertex W1,
In the right hand,
W2, Wn.
and X.
Okay.
No, with
And
X also.
And
X.
and
Including X.
Is everybody okay with this? Are you happy with what he's saying? Nobody seems happy.
I want to add one more edge.
No, please read read what I write. What's wrong in what I wrote?
W1, W2 up to WK may not be dominated. So if we add UI to WI edges also.
Yeah, we have no. UI to WI is also there.
Okay.
No?
Okay.
All I'm asking is this. Does U1 to UK will dominate every vertex in W1 to Wn, comma X? That's all that I'm asking. Is the question clear to you, Satya?
Yes.
Yeah. So I'm not saying they form a dominating set of G prime. I'm saying they form they dominate every vertex in the right side. Is this okay with everybody?
Yes.
Okay. So now what should we do to dominate everybody?
And X is there, since X is adjacent to every vertex in the left side, that is U1 up to UN. So if we include
So if you add X,
X,
implies X dominates every vertex in left side, right? So which implies that U1, U2, UK, comma X
is a dominating set in G prime.
in G. Correct. Okay. Now forward direction is fine. What about reverse direction?
So if there is a dominating set of size K plus 1, since there is there is edges between UI to WI. So if there is some vertex from W1 to Wn, we can exchange it by the corresponding UI vertex.
Why?
Like swapping to show
Why?
that.
And if you swap, and why are they so sure that if you swap, it will be okay?
Okay, now no need to. Okay, so there may be some U1, U2, and some Wi, Wj. We can take the corresponding vertices in G. Like if there is Wi.
What happens if okay? So say D is a DOM set in G prime. Let D intersection left hand side be some U1, US, where S is less than equal to K. Is that fine? Less than equal to K plus 1. Is this okay? But S could be also equal to K plus 1, no? Then what should I take? Whose image should I take? But for now, let's assume that S is less than equal to K. Okay. Now, D intersection left hand side. Okay. Let's call this D prime. Is say S is less than equal to K. Then I want to say that vertices corresponding to D prime in G is a dominating set. Is this okay? Okay. So suppose some vertex does not get dominated. So suppose this is D prime and some vertex does not get dominated. Okay. Some vertex does not get dominated. Why is not getting dominated? You tell me. Why this vertex does not get dominated? Who are these vertices? Okay, so suppose in D prime I chose some vertex. Okay, and what is the meaning some vertex does not get dominated? It means this vertex, okay, or rather look at this. If you choose a vertex here, they must dominate everybody in the right hand side except those that are picked here. So these vertices dominates everybody in the right hand side except which vertices?
Which are not picked.
Which are not part of your dominating set. So dominating set contains some black vertices and suppose it contains some green vertices, right? Now black vertex must dominate every other vertex but green vertices, right? It may dominate green vertices, it may not dominate green vertices. Okay. So the right thing would have been, as she was saying, is that you take, not only that, you take, what should you take D prime to be? you take D prime to be, okay, you take D prime V if either some Vi, if either Ui or Wi belongs to D, where D is a DOM set of G prime. So this is what he said, that if either copy is there, right, you just pick one copy of this, right? Okay, and then if D prime has less than equal to K, you should be able to show that this D prime is a DOM set in G. But why it is of size at most K? This is not clear to me.
So can't we say that if in the new G prime, if there is a dominating set of size K plus 1, and if it doesn't contains the new vertex X, then we just take the reverse mapping and it will give a
I don't know. You prove it. But or you could have also done something more funky and like just to ensure that.
Can we add something? K plus 1.
K plus 2. Just one. Just one.
Yes, one.
This is it. Then you know that from Z and X, you will always have to pick one vertex because otherwise, who will dominate Z? Right? So it is always better to pick X. There always exists a dominating set that contains X. Okay. And the forward direction will anyway hold because the moment you pick X, then you also dominate Z. Right? So now, if you said this, then you can say that D prime has size at most K, and then you're good.
Z is adjacent only with X.
What? Yes.
Okay.
Z is only adjacent to X. Z is a guard of X. Okay. What is Z? Z is guard of X. Okay. Okay. This is something simple. You should work it out yourself, please. I wanted you to give this idea that when you do this partitioning, then this is how you mimic the, what do you call, neighborhood relationship between partition. That's all that my motive was. The rest is like something which you must have seen or you will be able to work it out. Okay. So unless there is any further question, I'm done for the day.
I have a question.
Please ask.
So when we are talking about FPT, we say with respect to something like solution size or something. So when we are saying W1 hard, is that also with respect to solution size or something? Or it
yes,
is,
of course.
Okay.
Otherwise, it absolutely makes no sense.
Okay.
Hardness is, what is the meaning of hardness? Think. What I'm trying to say, I'm saying for this problem, I cannot design such an algorithm of such running time, that such running time always has parameter in it. So I can only say it's W1 hard for this parameter because a problem could be fixed parameter tractable with different parameters. Like for example, independent set is FPT with parameterized by number of vertices. Click is FPT parameterized by number of vertices. Okay.